Okay, so let's see what we've got now. The other thing which is shown on page 146, which you should also be aware of, is that we actually can do something, if we wanted to, about this dip here just by changing neutron energies. So for this kind of a situation, this involves thermal neutrons. But if we use a somewhat more energetic neutron, and on page 146, figure 8.3, they show you this where they're doing this now, first with the thermal neutrons that have energies of about 2 million electron volts. Then they've increased the energy to I'm sorry, this is the thermal neutron. Then the two MeV neutrons look sort of like this. And then finally, you get another situation where you get something that looks like that. And that's, I should probably show these in different colors. Might be a little bit easier to see. So you've got, this one is the 2 MeV neutrons here, and then you've got up on the top here, which is much more energetic, are these 14 MeV neutrons. And you see that for 14 MeV neutrons, now you don't have so much, you don't have this great discrepancy between asymmetric and symmetric fissioning. They occur in I won't say in the same amount, because you're still about 8%, 8 to 10% up here, and you're still about only 1% here, but it's still much more significant than the 0.01% that you had down there. So we find that as we go to greater energy neutrons, that we're actually going to increase the yield of these symmetrical products. Okay, there's something else that we want to consider, and that's something called the fission barrier. For fission to occur, the fission barrier has to be overcome. So and it turns out that not all even nuclides will undergo spontaneous fission, and not all even odd nuclides undergo thermal fissioning. It turns out that there has to be a sufficient energy which actually has to overcome the barrier to fission. Because what we're trying to do is we're trying to overcome the strong force that's actually between that's actually holding the nucleus together. So in order to fission it, we have to have a sufficient energy to overcome that force. So that's something that we have to consider. And there's a table that is shown on page 147 that addresses this. It's the relative tendencies to undergo neutron-induced fission for selected heavy nuclides. And it shows us something very, very interesting. Also, I want to call to your attention just the fact that for two different nuclides, if you're actually looking at if this is uranium-235, you can also superimpose on top of that what the thermal neutron fission product distribution would be for for plutonium-239, and you find out that the entire graph is shifted to the right slightly. So that's just something else that I call to your attention. But again, getting back to this table 8.1, the nuclides that are listed here there are 3 uranium isotopes, 1 plutonium, which is plutonium-239, and also thorium-232. And the 3 uranium isotopes are 233, 235, and 238. Now, what you've got alongside of the nuclide is something that says sigma sub F, and that's the cross section in Barnes for that particular reaction, which is for the fission reaction. that would be taking place for neutron-induced fission. So it's giving us really the relative probabilities for all of these kinds of reactions. So you'll notice that for thorium, it's the number is very, very small. It's 3 times 10 to the minus 6, I believe. And for uranium-235, it's much larger. To uranium-233, it's 5.30. For uranium-235, it's 5.86. And then for uranium-238, it's the same order of magnitude that it was for thorium-232. It's very, very tiny again. 3 times 10 to the minus 1, 2, 3, 4, 5, 6. 3 times 10 to the minus 6 again. And then for plutonium, it's higher again, quite a bit higher. And that's not, I think I said 5.30. That's again because I don't see very well. Now that I'm looking at it in a slightly better light, I see that it's not 5.30. It's 530 for uranium-233, 586 for uranium-235, and 752 for plutonium. So this is showing us the plutonium is slightly better at undergoing these reactions than either of the 2 fissile uranium isotopes, which are uranium-233 and 235, but much, much better by many orders of magnitude, like 8 orders of magnitude, uranium-238 and thorium-232, which do not undergo neutron-induced fission at all well. There's another, next to that, there's another column that says sigma sub gamma. And what that is actually, for this reaction, where you have an element, whatever it happens to be, in this case it was uranium, but it doesn't really matter, and it's the reaction where you've got you're absorbing a neutron and you're giving off a gamma. So it's that reaction that we're actually looking at, and then that goes to something else, goes to Y. So this is actually a neutron capture type of reaction, and you'll see if you look again at the table that for thorium that number's now quite high. So sigma sub gamma in Barnes is 737. So that's really telling us we have the 2 values now. We have this very low value, 3 times 10 to the minus 6 for sigma sub F, and then for sigma sub gamma, we've got this 737 value. And that's really telling us that this thing, thorium-232, is so much more likely to undergo a neutron capture. It's going to go to, it's 90-232, so it's going to go to 90-233. And then what will happen is it will undergo 2 sets of beta decay. So it's capturing a neutron, and it's going to undergo 2 sets of beta decay now, which are going to take it right up to, it's going to take us to protactinium, 91-233, and then there'll be another beta emitted, and that's going to take us to 92 uranium-233. So we actually, by irradiating with thermal neutrons, we can actually take thorium, which is a non-fissile isotope, but we can actually convert it into something that is fissile, which is uranium-233. And this is just analogous to what I showed you last time, where I took uranium-238 and did the same thing with it. And that's the other one, uranium-238. So remember, again, it had a terrible cross-section for fission, but again, if you look at the table, you'll see that it's got a nice high number, even, let's see what the number is for uranium-238. It's not as good as, no, it's not as good as thorium, which was 737, but it's still 99, so it's still a pretty high number. And so again, this undergoes, captures a neutron, goes to Neptunium, I'm sorry, goes to uranium. Well, that's the excited, that's the compound nucleus is 92, 239. That doesn't fission, but instead converts to 93, 239, which is Neptunium, through beta emission, and then beta emission again gives us 94, 239, which is plutonium. And this is a little busy. I've got a lot of stuff here. Let me just erase this so it's a little bit clearer. But that would give you your plutonium 239. So again, you start out with something that's fissionable but not fissile, and you wind up with something that is fissile in the end. And the other ones, as I say, the other plutonium, the numbers for that for both for both processes, for fission and for neutron capture, are quite high. 752 for fission and 269 barns for neutron capture, followed by gamma emission. And for the other two, uranium-233, the value is 48 for gamma emission and 2.7. I'm sorry, I'm looking at the wrong one. And I already said 99 for uranium-235. So there's still quite high numbers. Now the other thing you can look at in this table 8.1 is the difference between the binding energy of a thermal neutron in million electron volts and the fission barrier, which is what we talked about on the previous page. And you'll find out, you'll see very readily that the nuclides that are fissionable but not fissile are always going to have binding energies that are going to be lower than the fission barrier, which is to say that these things are not going to undergo fission. But if you look at uranium-233, where the binding energy is 6.8 and the fission barrier is 6.0 million electron volts, or for uranium-235, where it's 6.5 is the binding energy and 5.7 the fission barrier. And again, for plutonium, 6.5 is the binding energy, 5.0 is the fission barrier. All of those exceed the fission barrier, and therefore they are fissile. But thorium, which is 4.8 binding energy and 7.5 fission barrier, and uranium-238, which is 4.8 binding energy and 5.8 fission barrier, do not exceed those numbers. Okay, so we can also calculate. We can also take one of these reactions and actually calculate the Q value, which we did in a previous chapter for a number of reactions. And this is actually going to give us the energy of the lost mass in the reaction. So if we did this for the reaction that we were talking about, that is uranium-235 picking up a thermal neutron and going to uranium-236, just looking at the formation of the complex nucleus, we could calculate Q for that. And what we would do is just say 92 uranium-235 plus the neutron gives us uranium-236. And the Q value for this is the mass, so we have to look at the difference between the two masses. That is, look at this mass and look at the difference between that and the sum of these two masses. And when we do that, we find that we've got 235.043923 plus 1.008665. There's actually that neutron, and then subtract from that the 236, which is the value of this, 236.045562 units, and multiply that by the conversion factor, 931.5 million electron volts per mass unit, and we come up with a value of 6.54 million electron volts. And we can, so we have that number, and we can actually, if we also want to see the kinetic energy that's involved for the thermal neutron, we can calculate that as well. The kinetic energy is approximately equal, the kinetic energy of this excited complex nucleus is actually going to be approximately equal to the kinetic energy of the neutron, which is the projectile. So that's E sub kx So E sub kx is the projectile, and that's going to be multiplied by A sub x divided by the atomic mass of the projectile divided by the atomic mass of the complex nucleus, and that's going to give us approximately the E sub kc, and that turns out to be, once we've then gone and converted that into electron volts, it's a very small number. It's 0.0253 electron volts. So in this case, it's just about negligible. So therefore, we can say that the excitation energy is really equal to Q, which we had already calculated in the previous thing, which was 6.54 million electron volts is the excitation energy for this. It's that plus this very, very tiny fraction of an electron volt, which we don't even have to consider here. Okay. There's another problem in here. See if there's anything else in here that I wanted to talk about in this section. No, I don't think so. But there's a problem here to calculate the total energy of a fission reaction that is a very, very common fission reaction that occurs when uranium-235 fissions, and that is the production of barium and krypton. So these are pretty favored things. So I'm just going to continue along here, and we're going to get barium plus krypton. And we're going to get we're actually going to get three neutrons out of this, 3, 0, and 1. So krypton is 56 and 92. And barium is, krypton is 36 and 92. Barium is 56 and 141. So that should add up. That gives us 233 plus 3 is 236. So it does sum correctly. Then we can look at the mass of the reactants again, which is the U-235, and we're going to subtract from that the mass of the two products. That's the barium 56, which is 140.914406 atomic mass units, and the mass of the krypton, which is minus 91.926153 atomic mass units. Now we're not going to subtract 3 neutrons because we already put 1 in to initiate the reaction. So the net is 2 neutrons, 3 minus 1. So then we're going to subtract the 2 neutrons from that, and that gives us 2.01730 atomic mass units. And so the total mass loss in this is 0.186. It's approximately 0.186 atomic mass units. And again, we can convert that using our 931.5 MeVs per mass unit. We find out that that equals 173.3 MeVs, the total energy of decay. And we can look at the kinetic energies of each of these things. So the total kinetic energy is going to be, again, using the formula that was introduced right at the beginning of the book, is at the beginning of the chapter is 0.80 times the z products divided by the cube root of the sum of the cube roots of the masses, and that gives us 0.80 times 56 times 36 divided by the sum of the cube root of 141 and 92, and that gives us a total of, so the kinetic energy total is 166 million electron volts for that. And if we want to do it by each of the nuclides separately, we can do that, and we find out that 66 of this is 66 of this is from the let's see, which one is that? Just the 141 barium. Okay. So 66 of it is from barium. So K for barium equals 66. That means the K for krypton has to be the remaining 100 million electron volts. And that gives you the total energy. And you'll notice that there's about a 7.3 MeV difference here. And these are approximations, so that's why these things don't add up exactly. It's one of the reasons anyway. So the energy that we get out of this immediately, it's called prompt energy. And then because there are secondary events that occur, these things might be radioactive and they can emit beta particles, and there's going to be additional energy. We call that delayed energy. So we have prompt energy and delayed energy that we can look at separately. The approximate average energy values for thermal neutron fission of uranium-235 are given in table 8.2, and you can see that the fission products are 167 MeV, so about what we actually had calculated for the neutrons. They're 5 MeV for the prompt X-rays that are produced, not X-rays, gamma rays that are produced during this process. There's 6 MeVs. That gives us a total energy of 178 MeVs. And then the delayed energy, 8 MeVs in beta particles, 12 MeVs in neutrinos, 6 MeVs in gamma rays, and a total delayed energy of 26 MeVs. So if we sum 178 and 26, we'll get a total fission energy for this reaction. That's prompt and delayed energy of 204 MeVs. And we can do that. We can also look at, there's another example that's given here, which is to estimate the delayed energy for the fission products that are actually formed. The delayed energy, which would be the taking the barium 141 and looking at everything it decays into, and that's shown on the bottom of 150. So barium undergoes a series of 3 beta decays. It goes to lanthanum 141, and then it goes to cerium 141, and then finally it decays to the stable isotope, which is praseodymium 141. And so you've got an energy associated with each one of these beta emissions that occurs. And these are all added up, and for that particular, what do we get for that particular one? We'll find out that it's actually equal to 6.3 MeVs. And then we can do the same thing for krypton. So krypton actually undergoes 1, 2, 3, 4, not 3, but 4 decays. It goes from krypton 92 to rubidium 92 to strontium 92 to yttrium 92, and finally goes to zirconium 92. And as you would expect, since there are more beta particles, and these actually happen to be more energetic as well, we wind up getting a total, when we add all of those up, of 19.6 MeVs. And so the total energy here is going to be 25.9 MeVs. That would be the total delayed energy for that particular reaction. Okay. There is one other thing that's mentioned in here. It said before that in addition to using neutrons to promote fission, there's also something that's called photofission, where you can actually use high energy photons to promote this as well. And photofission occurs, well, it occurs actually, you don't see it all that frequently on Earth, you know, although we could actually induce photofission if we use high enough energy photons, you know, very, very energetic gamma radiation. But you see that, for instance, in stellar kinds of reactions, you see a lot of photofission taking place. So high energy photons can induce fission simply by transferring their energy to the nucleus, and once the nucleus absorbs enough energy, it will undergo fission.